Welcome back to another video. Let's jump right into the topic of continuous random variables. A random variable is a mathematical concept that represents the outcomes of an experiment or a random process. It's used to quantify the result of some uncertainty in an experiment. In simpler terms, a random variable takes numerical values based on the outcome of a random experiment. We use capital letters to represent random variables, which denote the quantity or property we are measuring in the experiment. For example, in your coin toss experiment, capital X represents the number of heads obtained in 10 tosses. On the other hand, small letters are used to represent a specific outcome or value of the random variable. For example, small x could represent a specific number of heads, like 5 heads. There are some important properties for discrete random variables that we need to pay attention to. The probability of any specific outcome, for example 0 heads or 1 head, must lie between 0 and 1. This makes sense because a probability can never be less than 0 or greater than 1. The sum of the probabilities for all possible outcomes of a random variable must equal 1. This is because, in any experiment, one of the possible outcomes must occur, so the total probability for all possible outcomes must be 100%, or 1. Random variables can be categorized into discrete and continuous types. A discrete random variable assumes a countable number of distinct values. In simpler terms, the values it can take are finite or countably infinite, like the set of natural numbers. As for the characteristics of discrete random variable, we can say that 1. The possible outcomes can be listed or counted. 2. The variable takes specific values, often representing counts, typically showing how many. And 3. These values are often integers or whole numbers. Examples include result of a football match. The outcome could be a win, loss, or draw, which are distinct and countable categories. The result is categorical. Number of tickets sold for the football match. This is a countable value. You can count how many tickets are sold, for example 100 tickets or 200 tickets. Since the number of tickets is a whole number, it is a discrete random variable. On the other hand, a continuous random variable can take any numerical value within a certain range or interval. The values are not countable as they can represent any value in a given range, including fractional or decimal numbers. In terms of characteristics, 1. The possible outcomes form an interval or a collection of intervals on the real number line. 2. The variable represents measurements of some kind, typically showing how much. And 3. The variable can take an infinite number of values within a given range, including values that are infinitely small, like decimals. As for examples, weight or height of fans attending the game. A fan's weight or height is a continuous variable because it could be any real number within a certain range, for example 150.5 pounds or 175.2 pounds. It can take values with decimals and isn't restricted to whole numbers. Total fluid ounces of drinks consumed during the football match. The total amount of liquid consumed can be any number of ounces, and it can vary continuously, for example 32.5 ounces or 47.2 ounces. The value isn't restricted to integers, making it continuous. A continuous random variable is one that can take an infinite number of possible values within a specific continuous range. For example, the amount of soft drink in a can or the weight of a student at a university can be any value within a range, such as between 0 and 12 ounces or between 100 and 200 pounds. Because these values are continuous, they can be infinitely precise, meaning there are no distinct steps between possible outcomes. One important aspect of continuous random variables is that the probability of the variable taking any specific value is 0. For instance, the probability that a can contains exactly 12.00011 ounces, or that a randomly selected student has a height of exactly 64.123123 inches is 0. This is because the set of possible outcomes is infinite, and the probability of landing on one exact value within that infinite set is infinitesimally small. Instead of calculating the probability of a random variable taking a particular value, we often focus on the probability that the variable falls within a specific range or interval. For example, Rather than asking for the probability that a student's height is exactly 64.123123 inches, we might ask about the probability that a student's height falls between 5 and 6 feet. The probability is then calculated for the entire range of values that fall within the interval, rather than for any one specific number. In summary, for continuous random variables, we rarely ask about the probability of a single value occurring. Instead, we consider the probability of the random variable falling within a range of values, and the probability of any specific outcome is always 0. For discrete random variables, the probability of an exact value can be non-zero. The point has mass. The distribution of a discrete random variable can be thought of as a series of probabilistic point masses. For continuous random variables, an individual value has no mass. The probability of continuous random variable x being equal to any specific number is 0. There is only probability in a range of values. The probability of a range of values is dependent on the density of probability in that interval, as there are no point masses of probability. A probability density function, PDF, is a function used to describe the probability distribution of a continuous random variable. It has several important properties that help to understand how probabilities are assigned to intervals of values rather than to specific values. First, the PDF must always be non-negative. This means that for any value of the continuous random variable, the probability density cannot be less than 0. The graph of the PDF always lies above the horizontal axis, representing the fact that probabilities cannot be negative. Second, the total area under the curve of a PDF must equal 1. This property ensures that the total probability of all possible outcomes for the random variable is 1. Since the random variable can take any value in the range, the PDF is designed so that the area under the curve over the entire range is equal to 1, reflecting the certainty that the random variable will fall somewhere within the range. Third, the probability of the random variable falling within a specific range is given by the area under the curve between the two values that define the range. For example, the probability that a student's height falls between 5 and 6 feet is the area under the PDF curve from 5 feet to 6 feet. This is the fundamental concept in continuous probability, where the probability of a single point, such as exactly 5 feet, is 0, but the probability over an interval can be a non-zero value. Additionally, the PDF itself does not give the probability of any particular value directly. Instead, it gives the probability density, and the probability of a variable falling within a specific interval is found by integrating the PDF over that interval. This integration process calculates the area under the curve between the desired limits. Discrete random variables assume a countable number of distinct values. This means that the possible outcomes of the random variable are separate and finite, or at least countable. Continuous random variables, on the other hand, can take any numerical value within a certain interval or a collection of intervals. The values are not distinct and can be infinitely precise, meaning they can take any value within a range. For discrete random variables, the PMF returns the probability mass for specific outcomes. This is because the set of possible outcomes is countable, and the probability of each outcome can be calculated directly. The PMF gives the probability of each individual outcome, and you can sum these probabilities for any desired set of outcomes. Since discrete variables have specific, distinct values, it is straightforward to directly compute the probability of each specific value. For continuous random variables, the PDF gives the probability density for a range of values, but it does not directly give the probability of a specific value, since that probability is always 0. The PDF is used to calculate the probability of a random variable falling within an interval. To get the probability for a given range of values, the PDF must be integrated over that interval. This integration process calculates the total area under the curve of the PDF, which represents the probability of the random variable falling within that range. Because continuous variables have an infinite number of possible outcomes within any interval, you need to integrate over the interval to sum the infinitesimally small probabilities that contribute to the total probability for the range. The cumulative distribution function, CDF, for continuous random variables is a function that gives the probability that the random variable x takes a value less than or equal to a certain value, such as x0. In other words, the CDF gives us the cumulative probability up to a specific point. For a continuous random variable, the CDF is defined as the integral of the probability density function from -infinity to the value you're interested in. This means the CDF is built by accumulating the probability density over the entire range of values up to a particular point. Since continuous random variables can take any value within a range, the CDF tells us the probability that the random variable will fall within a certain range, up to a specific value. CDFs are very practical for continuous random variables because it allows you to easily calculate the probability that a continuous random variable falls within a given range. To find the probability that the variable takes a value between 2 points, say, between A and B, you simply subtract the CDF value at A from the CDF value at B. This is much more efficient than directly working with a PDF, as you do not need to integrate the PDF over the range every time. The CDF is the integral of the PDF. This means that if you know the PDF, you can find the CDF by integrating the PDF from -infinity up to the value of interest. Conversely, the PDF is the derivative of the CDF. This means that if you know the CDF of a continuous random variable, you can find the PDF by taking the derivative of the CDF with respect to the variable. Intuitively, this means the PDF represents how the probability accumulates, or changes, at each point, while the CDF represents the total probability up to that point. Now, let's go over an example together. We know the time until a chemical reaction is complete, in milliseconds, is approximated by this cumulative distribution function. We want to know what is the probability density function, and what proportion of reactions is complete within 200 milliseconds. Please pause the video here to take a moment and try answering these questions on your own. To find the probability density function from the CDF, we need to take the derivative of the CDF with respect to x. By differentiating the CDF with respect to x, we can see that the PDF is 0.01 multiplied by e to the power of -0.01 x for non-negative values of x. To find the proportion of reactions that are complete within 200 milliseconds, we need to evaluate the CDF at 200. We are looking to find the probability of random variable x being less than 200, which is simply the value of the CDF at 200. The CDF of 200 is 1 minus e to the power of -2. So, the proportion of reactions that are complete within 200 milliseconds is approximately 0.8647. Please remember the practicality of CDFs for continuous random variables. A CDF enables us to easily calculate the probability that a continuous random variable falls within a given range. To find the probability that the variable takes a value between 2 points, say, between x1 and x2, we simply subtract the CDF value at x1 from the CDF value at x2. This is much more efficient and easier than directly working with the PDF, as you do not need to integrate the PDF over the range every time. For a continuous random variable x, the mean or expected value can be defined by integrating x multiplied by its probability density function over the domain of x. This formula can be extended to any function of x. For example, to find the expectation of x squared, you integrate x squared multiplied by its PDF over the domain of x. For the variance, you can use the definitional formula, which involves integrating the square of x minus the mean multiplied by its PDF over the domain of x. Alternatively, you can use the computational formula, which is calculated by subtracting the square of the mean from the expectation of x squared. Thank you for your attention, and see you in the next video.